RJC Soft is proud to illustrate to you the three-dimensional code IPSE. This code was developed by RJC Soft in collaboration with the research group of Enel, now grouped in Enel Energia ed Innovazione. Now RJC Soft continues the development and use of IPSE code. The IPSE code is a support for three-dimensional modeling, computer fluid dynamics, with radiative heat transfer and chemical kinetics, particularly useful in application to systems in which combustion takes place. This three-dimensional modeling, computer fluid dynamics, is a useful tool for setting and resolution of technological problems, particularly important for the phenomena of combustion in which the experimental approach is very expensive. Some typical issues that can be analyzed with IPSE are optimizing the combustion configuration, also for different load for the boiler to achieve a greater flexibility in use of the power plant. An optimal setup maximizes performance both in terms of cost, plant availability, and emission of pollutants. Other issues are analysis of thermal and chemical impact as a result of major changes in the combustion configuration. During the renovation of the main parts of the combustion system, it is important to assess the impact of these on the global and local behavior of the boiler. Other issues are use of fuel different from those of project and optional in admixture. For example, a coal boiler can be adapted to burn in part also biomass or refuse-derived fuel. It's important to check for any deterioration or improvement in boiler performance. A very important and often recurrent issue is related to fouling and slugging of the walls and of the heat exchange surfaces. Using solid fuels, we must deal with issues related to the ash deposit on heat transfer surfaces of the combustion chamber. A previous detailed analysis is often required. The IPSE code is also often used for the study of innovative combustion processes, for example, the gasification. Gasification is a process that converts organic or fossil fuel materials in syngas. The syngas is a mixture of carbon monoxide, hydrogen, and carbon dioxide and is itself a gaseous fuel. This is achieved by reacting the fuel materials at high temperature with a controlled amount of oxygen and steam without combustion. The gasification can be considered a source of renewable energy if the primary fuel is biomass or refuse-derived fuel. The gasification of solid fuels is an important tool for innovative combustion systems, in particular with the capture and sequestration of carbon dioxide. The gasification is important in the hydrogen economy as hydrogen source. You can also use the syngas exiting the gasifier to produce hydrogen directly, to be used later as a motor fuel or other. IPSE is able to treat even the reactions of gasification of coal, biomass, or RDF. Another innovative approach to combustion is the oxycombustion. The complete combustion with only pure oxygen is an innovative method that reduces the production of pollutant and may be important for the capture and storage of carbon dioxide. The fumes produced contain only CO2 and water. The equation of motion of the gas and the continuity equation provides the gas velocity vector field and the pressure scalar field. Energy transport equation provides the temperature field. For the correct setting of the problems of combustion phenomena is of fundamental importance the transport of energy by thermal radiation. Transport equations of chemical species that must contain the term related to chemical kinetics. Chemical kinetics must treat both elementary reactions in gas phase and heterogeneous reactions, the volatilization and combustion or gasification of coal, biomass, RDF. Now show some examples of typical applications of the IPSE code to industrial equipment. You can see in the first horizontal section the temperature scalar field and the gas velocity field obtained from a calculation of a combustion chamber with tangential burner oil fired. And in the second picture you can see the field of heat flux to the walls as calculated by IPSE for a combustion chamber with opposite burners coal-fired. Finally, in the third figure you can see the temperature distribution calculated for an industrial furnace for petrochemical process gas-fired in the vertical section. IPSE has been used for many analyses of the combustion chambers of installations of industrial interest. Among these, the applications to the combustion chambers of the power plant Montefalcone, Brindisi, La Spezia, Fusina, Tor Valdaliga Nord, Porto Tolle, Niederhausen, Puertellano, Puente Nuevo, Cercs, Escucha. We show in more detail some results relevant obtained for the combustion chamber of Enel's Fusina power plant. The combustion chamber is equipped with tangential burners and has 5 floors burners, with close-coupled OFA over fire air coupled with burners, and the main OFA. The power supply is pulverized coal. The total electric power is 320 MW. In the left figure you can see the temperature field in a vertical section near the burner exit. In the right figure you can see the distribution of CO concentration as mass fraction in the same vertical section. You can see the 5 floors of the burner's inlets and the main OFA inlet above these and near the nose of the boiler. The burner inlets are characterized by low temperature and high CO concentration. The main OFA inlets are characterized by low temperature and low CO concentration. Following the main burner inlets, you see the high temperature combustion zone. You can also see the gradual disappearance of CO with the progress of mixing with the air coming from the OFA inlets. In this figure is shown the gas velocity field in horizontal section near the third burner floor. You can see the burner inlets and 4 corners and the beginning of the generation of the vortex, which is characteristics of tangential boilers. In this figure you see the map of the total thermal flux on the wall of the combustion chamber. The walls of the combustion chamber are shown as if they were opened and viewed from the inside. You can see the high thermal fluxes from the main burner zone, which continues until the nose. Unit 3 and 4 of the Fusina power plant have been modified to allow the co-combustion of refuse-derived fuel, RDF, with pulverized coal. The RJC Soft with IPSE code performed some preliminary analysis for all phases of the project, in particular for the first phase, analysis of the residence time and temperatures in the combustion chamber, and for the second phase, study of configuration of separate injections of the RDF in the combustion chambers and analysis of the performance of the steam generator and definition of improvements. In the following slides we show you some results about this calculation. In this figure you can see the concentration of solid particles from RDF in a horizontal section in the first RDF inlet floor. You can see the entrance of RDF particles only by 2 opposite corners, A and C. We also see the entrainment of the RDF particles inside the vortex. The issues related to fouling and slugging of the walls of the combustion chambers are relevant to the study of the co-combustions, in particular with fuels derived from waste, which can also lead to corrosion problems. In this figure we report the estimated rate of deposit on the walls of the ashes from RDF. You can see the areas with high deposition rate in these zones lagging from RDF ashes, and corrosion phenomena can be developed. The RDF contains small amounts of chlorine. Chlorine is a small source of corrosion. The chlorine is released from the particles of RDF in gaseous form, then follows the flow field of the gas. For the study of the co-combustions with RDF, it is important to analyze the chlorine concentration and the distribution. IPSE code can do this analysis. In this map is shown the estimation of the concentration of chlorine near the wall. In these zones, chlorine corrosion phenomena can be developed. Now we illustrate some of the most recent application of the IPSE code to problems in industrial and research and innovation. Among these, the most important we have Torvaldaliga North power plant, Maritza 3 power plant, Siemens gasifier power plant, ITEA combustion innovative system, oxy-combustion innovative system, solar receiver research apparatus. In the figure are shown the temperature and the flow field calculated during the study of the ITEA combustor in industrial size. The Torvaldaliga North power plant has recently been converted from oil-fired 4 units to pulverized coal-fired 3 units. The main characteristic of the new units are combustion chamber with opposite burners, power with pulverized coal, 6 coal mills, 24 low NOx burners, 4 plus 4 burners times 3 rows, 8 over fire air ports, power 660 MW. The unit worked typically with 5 mills in operation in 1 mill standby. We analyzed 6 different boiler configurations related to the standby coal mills. On the background we see a photo of the new plant. In the figure at right, you see the temperature field with the gas velocity field on a vertical section in the center line of the second column burner. This figure shows the result for the cases where the mill A is standby. Each mill feeds only one row of burners. This slide shows the fields of the temperature and velocity of the gas in the same section of the preceding figure. These are calculated from IPSE for a plant configuration in which the mills C, F, and E respectively are standby. This slide shows the fields of temperature and gas velocity in a horizontal section at the first floor of the burners, floor fed by mills A and B. Are displayed the results obtained for the case where the mill A is in operation while B is in standby. The mill A feeds the burners on the front of the boiler, while the mill B feeds the burner along the back. You can see the motion field and temperature, typical of low-NOx burners in a single row nano post. Finally, this slide shows the fields of temperature and gas velocity in a horizontal section at the second floor of the burners, floor fed by mill C and D. These results are obtained from the same simulation of the previous figure. You can see the motion field and temperature, typical of low-NOx burners, in a double row opposed. We have studied the combustion chamber of the Maritza 3 power plant. This power plant is fed with lignite up to 55% of humidity. The Maritza combustion chamber has 8-volt burners that produce a field of motion of the tangential type. This is the typical configuration of boilers for lignite. The boiler has 8 mills with gas recirculation pre-dryer. The total electric power is 210 MW. We analyzed different configurations of mills and gas recirculation for verify gas temperature and to assess lagging problem in furnace and mills duct. In the figure is shown the gas temperature distribution in the horizontal section at the center line of the high section of the burners. In the two figures you can see the field of temperature and gas velocity in the vertical section at the center line of a pair of burners. In these two other figures we show the fields of temperature and gas velocity in the other vertical section at the center line of the combustion chamber. In the last two figures are shown the fields of temperature and gas velocity in the horizontal section at the height of the suction of the flue gases. The hot flue gases are sent to the mills to dry the lignite. A recent development of the code is his version of simulator. The IPSE simulator is a reduced version for timing simulation in helping the design and operation. Actually is experimentation with numerical simulation of a pilot plant for the gasification and can be used for analysis of design solution for the model of the pilot plant gasifier, characterization of the type of power supply to be used for the gasification process, coal and biomass, experimental analysis of simulation data obtained by feeding various percentages by mass of coal and biomass. The present implementation is for a model with a geometry based on data for a pre-mechanical design. The IPSE simulator uses a kinetic model for heterogeneous gasification on the geometry of the gasifier Siemens fed with 5000 kg per hour of coal. Processing data from the simulation of the geometry of the gasifier group compares to evaluate in terms of quality with a submodel Lagrangian flow dispersive solid phase on the walls of the gasifier. Simulation results are temperature distribution, velocity distribution, distribution of chemical species, distribution of solids. Examples of results are shown in the following slides. In these slides are shown the field of temperature and gas velocity in the horizontal section near the inlets of the system. It is noted that the actual calculation is performed on a quarter of the geometry in order to reduce the computation time with judicious use of the symmetry of the system. In these slides are shown carbon monoxide and hydrogen concentration fields in vertical section. The gas velocity field is superimposed. We recall that for the gasification process, hydrogen and CO are the main products. The following two figures show the distributions of concentration of solid particles of char, respectively for the particles of initial diameter lower and upper. It occurs as fine particles with lesser initial diameter are completely consumed, while particles with a greater initial diameter react only partially. In the last two figures we show the distribution of ash concentrations on the left and the field of temperature and gas velocity on the right in the usual vertical. For better management of IPSE simulator, RJC Soft produced the Dixit interface. It is the interface for the user to the simulator of the gasifier realized with IPSE simulator previously illustrated. It manages the dynamics of global variables that generate the input boundary conditions for the IPSE simulator, so the user can check the status and progress of the simulation of the gasifier. It maintains the value of global variables calculated by IPSE and provides to show as function of time in graphic form. It is a prototype for a scheduler for processes coupled in series and/or in parallel, which will be extended to other simulators processes. Here you see the main screen of Dixit. There are controls timings for the beginning and the end of the simulation. It has the selection of variables in input to the simulation to be assigned, as well as the selection of the output variables to be displayed. With the interface Dixit, the values of the input variables to IPSE simulator are assigned in function of time. As an example here, it is shown a step change in the oxygen input flow rate to be made at 30 seconds from beginning of the simulation. Dixit keeps the timeline of the main values calculated by IPSE simulator. The Dixit interface displays the main results obtained through IPSE simulator in function of simulation time. Here is shown the variation of the concentration of CO existing in the gasifier in response to the variation in the flow of oxygen previously illustrated. In this slide we show the variation of the mean temperature of the gas exiting the gasifier in response to the variation in the flow of oxygen previously illustrated. Dixit coupling with a two-dimensional viewer, you can get maps of the usual scalar and vector fields calculated by IPSE simulator. As an example, here it is shown a map of pressure distribution obtained at the end of the previously illustrated transient variation. To conclude this presentation, we can say the three-dimensional code IPSE provides the maximum degree of information currently obtained when used for the analysis of an industrial system in which combustion takes place. The IPSE code helps designers and plant operators in choosing the best solutions, both from the point of view of thermal efficiency and of reduction of pollutants. IPSE proves to be a useful tool for implementation of innovative P.R.I.M.E, project of smart charging for electric mobility, which in Italian means Progetto di ricarica intelligente per la mobilità elettrica. To study the impact of electric mobility in terms of reduction of pollutant and impact on electrical system, RJC Soft developed the software P.R.I.M.E based on the request of Enel and of the Ministry of Environment and Protection of Land and Sea, and with their collaboration. This software was used for modeling the individual electric mobility with specific mathematical models to study the environmental impact and energy efficiency achieved on a large-scale scenario. P.R.I.M.E is able to quantify the possible benefits deriving from the use of electric cars in terms of reduction of greenhouse gas and other pollutant emission due to electric mobility, and in terms of impact on the electrical system caused by the increased demand for energy due to charging electric cars. The reference scenario is based on the vehicle fleet of 2012 in Italy. From this, the following scenarios consider different substitution of internal combustion engines with electric vehicles. The replacement leads to a reduction of pollutants produced by vehicles, but at the same time increases the demand of electricity production. For the study of mobility impact, vehicle categories were divided into 4 types: internal combustion vehicles, hybrid vehicles plug-in, electric vehicles. Each one of these categories has different properties that the user can modify to change the characteristic of the different scenarios. The following slides are examples of the screens of the software that the operators use for setting the characteristics of vehicles. This slide shows an example of the tables that contain the properties of electric vehicles and, as for the hybrid vehicles, their charging curve. The users can modify the present characteristics and also add other types of electric vehicles, providing all the required specifications. To add new electric vehicles, the operators can use different methods: add manually or add from file. The software could calculate a lot of the scenario's characteristics. As an example on this slide and on the following ones, we report some of the results. The software P.R.I.M.E can calculate the rate of emissions avoided with the use of electric cars and the pollutant emission produced by power plants supplying the additional electricity production, as we can see in the table. As part of the economic calculation, P.R.I.M.E can make an estimation of the primary fuel consumption and the associated costs. The estimation can be done both for mobility consumption and to produce the additional electricity. The software P.R.I.M.E can also evaluate the cost of pollutant emissions produced both from mobility and also from production of electricity with extern methodology European Commission. The software, using the values of the costs of polluting emissions obtained through the method extern, produces a bar graph shown in the figure. Another two graphs obtained with the software P.R.I.M.E demonstrate the trend of the request of additional electricity and the trend of global production of Italian power plants, both on 24-hour base. The goals of the software are giving scores to the different scenarios to understand if the replacement of the internal combustion vehicles with electric ones is convenient or not in terms of emissions and cost avoided, and also compare more scenarios via scores to understand which are the best ones. On the bar graph on the right, there is an example of the comparison of two different scenario scores. As a conclusion of this RJC Soft presentation, we can state that P.R.I.M.E is a useful software for the study of the impact of increased electric mobility in terms of the behavior of the power grid, production of pollutants, and actual costs for primary fuel and for the environmental impact. On this presentation, RJC Soft is discussing about the software systems developed by us based on the functionalities provided by DMSs. First, we will analyze the main features of such platforms, and then we will focus on our work that exploit these systems. Document management systems, also known as DMSs, are software platforms that aid in the publishing, storage, indexing, and retrieval of documents. They help the companies to manage all their content and control their business processes. Some of the most important and useful features they provide about the documents management are storage and classification, searching and retrieval, versioning, administration, security, and workflow management. In more details, the documents are stored in the system and identified using the metadata so that every document can be retrieved later. A metadata is data about data content, and it can include keywords, date, author, or other attributes. Search functions can be more or less sophisticated, allowing searches by elements of the document's metadata or by searching the actual document for keywords or phrases and using semantic analysis to determine relevance. Storage and management of different versions of documents is useful for documents that require frequent updating. It allows authorized users to return to earlier versions. Users require different levels of authorization, with certain more sensitive functions or documents being available only to selected users. It allows authorized users to return to earlier versions. Users require different levels of authorization, with certain more sensitive functions or documents being available only to selected users. Finally, the system allows an administrator to create a rule that dictates the flow of the documents through an organization. We developed several applications based on different DMSs, such as IBM FileNet and Alfresco. Our customers are both big companies such as Eni, Snam Rete Gas, and Enel, and local municipalities. Each project concerns a complete management of the documents, but the main purpose is different. We talk about 3 examples, each one's based on a different aspect such as document storage, task assignment, and legal files production. The first example is a system based on FileNet that has the aim of the document storage. So, the most important functionalities it supports are massive storage, metadata creation and management, full-text search functions, accessing lists, and implementation of permissions. The second example is also based on FileNet, but its goal is the tasks assignment. Main features are rules-based workflow developing, versioning implementation, and users' permissions management. Finally, the third system is based on Alfresco, and it manages the production of legal files. The functionalities it provides are tax algorithm implementation, workflow management, and document storage. International Flame Research Foundations and Livorno Test Facilities. IFRF is a non-profit foundation managed by its members' representatives. IFRF vision is to be the international reference point for clean and efficient industrial combustion. Its mission is to advance applied combustion research and promote cooperation and information transfer throughout the international combustion community. From this slide, you can see how IFRF Foundation from 2007 is structured. The IFRF membership base is organized around 8 national committees and the associated membership group. During 2011, member numbers remained relatively stable at around 130 industrial and academic organizations across Europe, America, Australia, and China, representing 1,500 individuals. Here following the name of the Joint Committee members. The President, Dr. Jacques Duguay, total France. Vice President, Professor Hartmut Splithoff, TUM, Germany. General Secretary, Dr. Sauro Pasini, NL, Ricerca Pisa. Superintendent of Research, Professor Neil Fricker, Glamorgan University, UK. On this and on the following slides, there are some works of IFRF and some results that Foundation has obtained. IFRF is a non-profit foundation managed by its members' representatives. IFRF vision is to be the international reference point for clean and efficient industrial combustion. Its mission is to advance applied combustion research and promote cooperation and information transfer throughout the international combustion community. The IFRF membership base is organized around 8 national committees and the associated membership group. During 2011, member numbers remained relatively stable at around 130 industrial and academic organizations across Europe, America, Australia, and China, representing 1,500